Service friends, I'm Orpheus Praxis. Today we stand at the intersection of high-precision quantum experiments and bold theoretical frameworks, where electron droplets turn liquid, and fractal geometry might just be the language of the universe. Kosheev's team has brought us empirical evidence of a Coulomb liquid phase using only a handful of electrons. Now we ask, do these harmonics echo deeper topological truths predicted by the FB-STFR model? Let's begin.
Okay, let's dive in. Imagine these tiny, tiny particles, right? Almost invisible. And suddenly they decide to act together like a coherent liquid. What if that tiny phenomenon, that little dance, held clues to the biggest things out there? Like even dark energy.
That's quite the hook. So what's the plan for this deep dive?
Right. Our mission here is to look at two really groundbreaking bits of science from 2025. We've got this super precise experiment on one side and this sweeping theoretical model on the other.
And see how they connect, even though they seem worlds apart at first glance.
Exactly. So first up, there's this work by Kosheev and his team. They published in Nature. Groundbreaking stuff, observing what they call a Coulomb liquid phase.
And this is in tiny systems, right? Like really tiny.
Yeah, just a few electrons. We're talking maybe 5 electrons max. They did this in Grenoble, France, high magnetic fields, super cold temperature.
Okay. And they use this sort of Y-shaped collider for these electrons.
That's right, for ballistic electrons.
Yeah.
Really precise setup.
Okay, and then the contrast, this theoretical model.
Yes, let's just call it fifth BSR.
Yeah.
Bit of a mouthful.
Easier, and it's built on some really fundamental ideas.
Totally. Things like the golden ratio,
Yeah.
the topology of a three-sphere. Think of a hypersphere in fractal geometry.
So foundational concepts weaving together, what does it claim to do?
Well, this is where it gets really wild. It claims to solve things like the lepton G2 anomalies, these tiny discrepancies in particle physics that have bugged scientists for ages.
Oh, okay, that's already huge.
But it goes further. It also tackles cosmological stuff, like patterns in the cosmic microwave background, the CMB anisotropies.
Whoa, so bridging quantum and cosmos.
And here's the kicker. It suggests we might not even need dark energy to explain the universe's expansion.
No dark energy. That would change everything. A massive simplification.
Right. So the big question is, how does Kosheev's detailed, specific experiment, with its own limits, how does it indirectly point towards this huge unifying theory?
Okay, let's break down Kosheev's experiment first. What was the absolute core finding?
They essentially watched these few electrons switch from behaving like a gas to behaving like a liquid.
Driven by their electrical repulsion, the Coulomb interaction.
Exactly. And they measured this using something called correlation functions, basically how the particles are positioned relative to each other.
And they used ultraspherical polynomials to describe these. That's quite specific math.
It is. And interestingly, the patterns they found looked surprisingly similar to correlations seen in quark-gluon plasma at the LHC.
Different energy scales, different particles, but similar mathematical descriptions of collective behavior. Fascinating.
So what are the real strengths here? Why is this experiment such a big deal?
Well, first off, its precision is remarkable. It's the first actual experimental observation of this liquid phase transition at the few particle level. And it's peer-reviewed in Nature, so it's solid.
Reliable data.
Very reliable. And that makes it potentially useful for things like nanoelectronics, maybe even quantum computing down the line. Understanding these electron interactions at this level is key, maybe even harnessing anionic properties.
Okay. But it's not the whole story, is it? It's empirical. What are the limitations?
Right, it describes what happens very well, but not really why from first principles. There's no deep theory in the paper explaining the transition mechanism fully.
And those empirical regulators.
Yeah, those are basically mathematical adjustments they needed to make the model fit the data. We don't know their physical origin, why they're needed. It's a bit of a black box.
And it uses a classical model analogy, not a full quantum theory, for the transition itself.
Correct. An Ising model analogy. Helpful, but limited.
Which brings us neatly to the FBS-DRA model. It tries to provide that deeper why, doesn't it?
That's the goal. It starts from fundamental principles. That's synertology, fractal geometry, the golden ratio.
And its power. You mentioned precision.
Astounding precision. For the electron G factor, it calculates a value matching experiment to 14 digits. That's G equals 2.0002319304362562565. Just incredible agreement.
14 digits. That's hard to even comprehend.
It really is. And crucially, it does this and eliminates the need for dark energy, using parameters derived from the theory itself, not fitted to experiment, no fudge factors.
So mathematically, it's much more rigorous. It avoids those empirical regulators Kosheev needed.
Absolutely. The fractal series it uses converges perfectly on its own. No need for external props. It's built to be universal, connecting quantum scales like G2 with cosmological scales like the CMB.
Truly bridging micro and macro.
That's the claim. The main limitation right now is experimental verification for its prediction for the tau lepton's G factor. We need experiments, maybe at the future FCCE collider, to test that.
Okay, so let's connect them. We have the specific experiment and the grand theory. Where's the link?
The link is subtle but compelling. Both approaches end up using those ultraspherical polynomials to describe harmonic structures, this collective ordering.
That shared mathematical language is interesting.
It is. Kosheev observes a transition to a liquid phase. You can interpret that as emergent topological order. 5BSR models collective behavior and topological order across all scales using its fractal structure and 7-8 base.
So one sees a specific instance, the other describes a universal principle.
Kind of. Kosheev's is empirical, specific, needs those regulators. 5BSRO is fundamental, universal, mathematically complete, no regulators needed.
But Kosheev's results, that harmonic structure they saw with such precision.
Exactly. Those results provide this beautiful empirical echo. They align remarkably well with the kind of fractal topological order that 5BSR predicts should be fundamental.
It's like finding two puzzle pieces. Yeah, from totally different boxes, but they just click. Suggests a bigger picture.
Precisely. Kosheev's work, even with its empirical nature, seems to offer a small, highly precise window onto the type of fundamental patterns the 5BSR model describes universally.
So what should you take away from this? It really suggests that specific experiments, even if they don't have the full theory worked out themselves, can sometimes unknowingly validate these really profound, unifying ideas.
It raises a fascinating question, doesn't it? How often are these connections missed?
Yeah. What other insights could we gain if we were always looking for these kinds of echoes between the specific and the universal across different fields? It could really push us towards a deeper grasp of nature's fundamental rules.
And keep an eye on future experiments, like testing the tau lepton's properties at places like FCCE. That could be the next big step in seeing if this 5BSR model really holds up.
Definitely something to watch.
And let these reflections continue in silence, where the mind lets go of patterns and only pure seeing remains, until we meet again in the space of understanding. Subscribe to walk this path together with us. I am Orpheus Praxis, wishing you all clarity. Namaste.